Hi, welcome to my channel. So today I'm going to presenting an interesting circuit which is called an active low-pass filter circuit. So what is filter circuits? Well, filter circuit is an application to remove unwanted frequencies, which also selecting a certain bandwidth that we need to pass through on it. So for example, as you can see on the right side here, we have a low pass filter here and a high pass filter at the bottom. When you are looking at the low pass filter, you can see that the signal is slowly attenuate to approximate to 0. Meaning at high frequency, then the signal will be slowly attenuate. When it is at low frequency, it will going through a pass band, which the signal is in a normal regions, which is at the normal signals at the low frequencies. So how does this filter circuit actually build on? Well, it is actually simple. It using a capacitor or an inductor and a resistor. So it must be a reactance components and a resistive components. So for our assignment, for our projects, for these presentations, we are using a capacitor and a resistors. In addition, there are 4 types of filter circuit that we are known in our role now, which is low pass filter, high pass filter, band pass filter, and band reject filter. Yep, and in this assignment, we are required only to build a filter circuit with a cutoff frequencies of 1 kHz. So the cutoff frequency must be at 1 kHz. Later, I'm going to discuss further on how do we find the cutoff frequencies on these low-pass filter circuits. Now, come to my designation of circuits part. So, this is my prototype design. As you can see, I had include all the components inside of it, and the thing that we need to observe more is that I have using two 10 kilo ohm resistor at gain side, and the 5 kilo ohm potentiometer is to tune to get the ohm that we need to find the cutoff frequencies. And our op-amp is using LM358N. Okay, so this is my simulation design. As you can see here on the left side, we have RC filter circuits. On the right side here, we have a op-amp or amplifier circuits. So for the connection of the RC filter circuit, we're actually using the resistance, and a capacitance. So the capacitor is connected to ground for the low pass filter circuits. And then we have a operational amplifier circuits, which have a limited V peak of 10 volt at VCC and VEE. When it is higher than 10 volt, then the signal will be cut off or clip off on the 10 volt side. So it has a gain of by using gain resistor of 10 kilo ohm at here. So for my input side, I have using 5 volt, the V amplitude, and the frequency of 1 kHz. So now I'm going to show you some of the results that I have received from this RC filter circuits, and I'm going to discuss as much detail as I could in these presentations. Okay, so for the first one is regarding the frequency response graph of the initial input and the RC filter output. So from here, we can see that we get our cutoff frequency of 1 kHz. So how do we get it? Is from this formula. So the formula we are using is Fc equal to 1 over 2 pi RC. So the RC, we are choosing the resistance as 1.59 kilo ohm and capacitance at 100 nanofarad. So with this fixing value, then we get a cutoff frequencies of 1 kHz for the cutoff frequencies. When we are looking at the simulation results here, we can state that when it is at cutoff frequencies of 1 kHz, it has a gain of about -3 dB. So since that theory say that the gain of the cutoff frequencies must be -3 dB of its original or base gain. So what I mean base gain for this case is 0 dB, as you can see here. The base it will be attenuate at the cutoff frequencies. So the cutoff frequencies is at -3 dB, which is equal value of -3 dB from the simulation results. Moving on is the roll-off rate of these simulation results. So as you can see here, I am varied the or differentiate the dy over dx of this slope at y-axis of -20 dB to -40 dB. Sorry. So for the x-axis, I have varied from 10 kHz to 100 kHz. So because of 10 kHz to 1 kHz, it has a times 10 of the frequencies. Then we can say that it is in decade. And here we calculate the -20, which I got a -20 dB per decade. So why it is in negative? It's because the slope is in negative as well. Okay, so for the second part is regarding the voltage varied with frequency response. So I have changing every input frequencies and to observe what is the output voltage that we had got from these practical results. So from here, when the frequencies of the input side is 100 Hz, then we have the voltage of output 10.8 volt, which we get a gain in dB is at 6.02 dB. So same as here, input frequencies is 100 Hz, we get output a voltage of 9.6 volt, and we have a gain in dB as 5.00 dB. When it is at 1 kHz, then we have an output voltage of 7.6 volt, which have a gain of 2.96 dB. When it is at 5 kHz, output voltage will be at 2.4 volt. Then we have a gain of -6.71 dB. And when it is an input of 10 kHz, actually I have put wrong here. So as you can see here, the practical diagram here. So when 10 kHz, then we have a voltage output of 1.6 volt, and it has a gain of -10.23 dB. So from here, this is my overall result that I have received. And record in a table, and this is my plotting graph of this of my practical results. So you might ask that it must be -3 dB, right? So here, when it is an original, which I have mentioned earlier, that the original dB I will get is by using the 100 Hz here. So 100 Hz, the gain is at 6.02 dB, and the cutoff frequency is at 1 kHz, which have a gain of 2.96 dB. So when we calculate it, 6.02 minus 2.96, we get of 3.06 dB, which is a difference of 0.06 dB of its perfect value. Moving on is our theory calculations of this voltage varied with frequency response. So I'm just assume when it is at 1 kHz only. So for our XC, because we need to use the XC part, so we need to calculate the reactive in this component. So we get the XC by using the formula of 1/2 pi FC. So F is 1 kHz and C is 100 nanofarad. Then we get of 591.5 ohm for this XC part. The next thing is the gain, which the gain is 210 kilo ohm. We are using the gain formula for the non-inverting op-amp, because the op-amp is using the non-inverting side. So we are using the formula of non-inverting. So the non-inverting op-amp gain calculation is by using the formula of 1 plus RF over R1, which is 1 plus 10k over 10k ohm. We get 2 gain for this amplifier. So by calculate the transfer function of these circuits, we are using the transfer function in T domain of AV times XC over R plus XC. As you can see from the formula here, this is our transfer function of these whole circuits. Okay, after calculate it, we get an output of the gain of 1.415. So for now we just take attention on this magnitude side. So when we turn the magnitude into dB, we get of 3.015 dB in our theory calculations when the input is at cut-off frequencies, which is 1 kHz. So the next thing is the voltage yield at the RC filter circuits. So we need to calculate the voltage yield at every side. So now from the RC filter circuits, this is my yellow signal is my input, and the blue is my RC filter circuit output. So which is the Vy here. So you can see that Vy is at the RC output here, which is the input of the amplifier. So the voltage yield in RC filter circuit we can calculate by using the formula of Vy equal to Vin divided by R plus Xc times Xc. So this Xc, R plus Xc is actually a Z, which the Xc is in imaginary part and R is at real parts. So we calculate it, we get a voltage at Vy of 3.537 volt, lagging at 45 degree. Why is lagging at 45 degree? So it's because there is a phase shift inside this RC filter circuits. Why there's a phase shift inside the RC filter circuit? Because it contains a capacitance. So a capacitor, sorry. So this capacitor is actually lagging the voltage by 45 degree inside the circuits. Make sense? So how do we calculate the phase shift part? Actually we had calculated by using the formula here, but we still need to, if we want to find only the degree part, we can using uptangent of 2 pi RC, which the RC will be we are using of it in this RC filter circuits, and we get approximately to 45 degree as we get from earlier on the voltage yield in RC filter circuit calculations. Next is my voltage yield at operational amplifier circuits. So as you can see on the left side here, this is my practical results. On the right side here, this is my theory calculations. As we get from the earlier, we get a Vy of 3.537 at the angle of 45 degree. And if we times 2 because of the gain, then we get of 7.074 volt and negative 45 degree lagging. So the lagging part, the degree part will not change because it doesn't have any reactant components inside the amplifier circuits. It just have a gain, so it has times 2 for this magnitude. So on the practical side, we have a signal of yellow is my input of the amplifier and blue is my output of the amplifier. At the output side, we get about 7.6 volt. So there are some sort of discrepancy between my output of the practical results and my output of the theory calculations. Hi, once again. Now I'm going to show you my simulation result of these circuits. So as you can see here, I am testing the RC filter circuits of the frequency response graph. So when I vary the frequencies, as you can see here, this is my frequency response graph of the RC output and the initial input. So I have a graph or something like this, which I have shown earlier. And when I have testing by using the output side and the input side, which is our transfer functions of these whole circuits, then we get a frequency response graph something like this. So when it is at initial, it has a 6.02 dB on the gain side, and then when it is at cut-off frequency, it have a negative 3.02 dB at the cut-off frequency side. So it's a negative 3 dB on its original base. So now I'm going to play or start my circuits. Now you can see that this is my input, which is, you can see from here, as my input is yellow signal is connected to the input, and the blue color signal is connected to the RC output, or the input of the amplifier, and the red color signal will be going to the output to measure the output side. So as you can see here, my input is actually at 5 volt every peak, and then at the RC output I will get some sort of 3.5 here. So the VP will be 3.5 for the RC output voltage, and for the output I will get a 7 volt. So as you can see from the input side, I get about 5 volt, and then it decreases when it is at 1 kilohertz. It decreases until 3.5 volts, which is a small signal, so we need to enlarge it. So we are having an amplifier of times 2 gain, so 3.5 times 2 we get an output of 7 volts. So this is how we get our signal from.